All right, welcome back again, everyone. This is MTED 110, and today we're going to be covering lecture 4A. So we're starting chapter 4. We'll do 4A and then 4B. This chapter is all about the actual algorithms that we use to compute. So this is a really fun chapter because this is where you'll learn how to do all of those tricks, you could say, or you'll learn how to use an addition algorithm that's a little more intuitive, or my favorite is the multiplication algorithm or the division algorithm. So this is all about algorithms, you could say. And there's some other models tossed in as well. Let me go ahead and pull up the slides and we will get started. Okay, so yeah, chapter 4, some conventional ways of computing. The one thing I should say about this, these are conventional because these methods have been around for a very long time. You might not have known about them, but that doesn't mean that they haven't been around. Uh, I honestly had not been taught a lot of these when I went through the K-12 education system when I was younger. So I was really excited to learn these when I was in college. But it's unfortunate that I only learned these in college, as you'll see. Okay, so some preliminary things. First, you need to understand our base 10 place value system. It's critical to being able to do arithmetic operations. So one of the things I've said in the past is that if students are struggling with a computational algorithm, a lot of the time it's because they don't really understand our numeration system well enough. And I have this little example here because there was a student that I was working with in intermediate algebra at LBCC, and the problem was something like this. I think we had to compute um, something like 245 divided by 5, right? And I was like, okay, so you could reduce that, you can cancel some factors, what would you do? And they were like, oh yeah, yeah, and they went like this. And they said, oh, this must equal 24. Now, when that student did that, what I realized is that it gave me an insight into how well they understand our numeration system and how well they understand these types of symbols. So what they were doing here is they were playing a game of symbols, right? They thought that because you saw a 5 on the top and a 5 on the bottom, that you could cancel them. And then what's left over are the remaining symbols. But that's not correct at all. So this is a student that made it all the way through K-12 but still doesn't really understand these fundamental concepts. And frankly, that's just a real shame. Like that should never happen. You should never be able to get through that much math education and not understand these types of basic concepts. So when I saw this, we had a conversation and I came up with some other worksheets that they could try just to see if maybe I could bring them up to speed. But this is the type of stuff you want to look out for because this type of example shows that a student is locked into the numerals. They don't understand the numbers that are going on here. They're only thinking of numerals, they're only thinking of symbols, and they're only thinking of pushing them around. And that's why it's a dangerous game to play, because then you can get pretty high up and still be making these mistakes. And having these mistakes pop up even now as you get older, it's always going to hold you back. It's going to hold you back. So we want to make sure that the kids learn this stuff very, very early on. And this is also why we spent so much time talking about chapters 2 and 3. Just a reminder, being able to execute an algorithm correctly does not mean that a student understands the underlying mathematics. So in other words, just because a student knows how to do, say, the division algorithm, that doesn't mean that they understand what's going on when they divide. And maybe they're just pushing the symbols around and they're really, really good at that type of symbol manipulation. But then eventually, stuff like that'll happen. Um, the way that we can get around this is by modeling the operations in several different ways and helping young learners make sense of the operations. So that's what chapter 3 was all about. Chapter 3 was all about how to model addition, subtraction, multiplication, and division. Now we want to go straight to algorithms. We want to talk about algorithms. The other thing is this: if you introduce students to several computational algorithms, it gives them a robust perspective of the operations. So we don't want to just teach them the standard algorithm or the expanded algorithm or some other algorithm. We want to teach them all of the algorithms. Okay, so we're going to start with addition. And earlier we saw some techniques that can make adding easier by splitting things up, for example. Now we're going to explore the standard algorithm and some variations of it that may be easier to follow. So here's a side-by-side comparison. Let's look at the standard algorithm first. I'm just going to zoom in on this kind of pixely picture here. So this is exactly what you would do if you wanted to add 37 plus 28 using the standard algorithm. So what do? You add the ones, and then remember you're supposed to carry this one, right? You're supposed to carry this one and put it up top right there. And then you write 5 down here. Oops. You write 5 down here because 7 plus 8 is 15, and you write the 1 up top over in the tens column because there's 110, right? And then the next thing you do is you add the next column. You add the tens column, 3 plus 2 plus 1, that's 6. And then your final result is 65. Now, it's not too bad of an algorithm. I'm assuming you all know how to do that. I'm not going to test you on being able to do that type of thing. We're going to learn some new algorithms that are a little more interesting, I think. This algorithm is totally fine, but the expanded algorithm, I think, is actually a little bit more, I don't know what the word is. I don't want to say convenient. Maybe contained? I'm not sure. Let's take a look, and maybe you can come up with a word to describe it. So the standard algorithm looks like, or sorry, the expanded algorithm looks like this. So now, this is what we call the expanded algorithm. And the idea is this. You first add the ones, but you just write the number that you get underneath. You write 15. And then what you do is you add the tens. And then you add the number that you get underneath. That's 50. And then you can add those together and you'll get 65. Now, the interesting thing about this algorithm is that there was no carrying or moving a 1 anywhere. The results were nicely stacked right below. And the critical recognition, or the critical thing to recognize here is this. Oops, is this. That's 50, not 5, right? So when these two values, 3 and 2, were added, they totaled up to 50 because that 3 is in the tens place and that 2 is in the tens place. So that's why it's not 3 plus 2, it's 30 plus 20, which is 50. So that's the key idea there, right? And you can see right away that you need to have a comfortable understanding of the base 10 system, right? So that's the expanded algorithm. We can do another one. It's not that hard. How about, let's see. How about we do something like 26, I can write that better. 26 plus, we'll say 57, okay? All right, so we're going to add those up. What's 6 plus 7? 6 plus 7 is 13, right? So we're just going to write 13 below. That's all we're doing. We're just writing 13 below. And then, oh, let me zoom out again. There we go, 13 below. And now that we've done the ones, let's do the tens. Now we're not adding 2 and 5, we're adding 20 and 50. So we're going to end up with 70, and we're just going to write 70 down below. And then we're going to add those up, and we're going to get 83, and that's the result. And that's the result. Pretty cool, huh? I think that's pretty cool. All right, so that's the expanded algorithm for addition. Nothing too fancy there. Oh yeah, so one note, we want to avoid using the word carry. We want to avoid using the word carry. And why do you think that is? Let's think about it for a minute. Why would we avoid using the word carry? Not sure. Well, talk about it. Talk about it out loud with yourself. Talk about it out loud with your group members. Talk aloud about it out loud with somebody, right? And see, why would we avoid using the word carry? Okay, well, let's think about it. We're avoiding using the word carry because there's no real reason to, or I shouldn't say this, we're not really carrying a 1. So a lot of times people will say, oh, carry the 1. But the problem with that is that you're forcing the student to focus only on the numeral. You're saying, oh yeah, do you see that symbol there? That little symbol, the 1 symbol? Just put that symbol on top of those other symbols. Carry the 1 over there and everything will work out fine. But that's divorcing the student from understanding what's going on. You're not carrying a 1, you're regrouping a 10. That's what you would say. So instead of carry the 1, say something like regroup the 10. Or something like that. That's exactly what's going on. It's a regrouping. It's not a carrying, right? So try to avoid using the word carry just because that tends to point students onto the numeral way of thinking about things instead of the number way of thinking about things. Okay, so let's try a couple. Let's use the expanded algorithm to compute. Actually, that one, I'll tell you what, you should do this one on your own. Do this one on your own. Use the expanded algorithm to compute 824 plus 197. So I'll give everybody about 10 seconds to practice that. Okay, and now let's do this one together. The next one says to use base 10 blocks to compute, and we're going to do 37 plus 28. And I'll show you why this is so important. Let's do 37 plus 28. Wait, where's my, there we go. So 37 plus 28, and we computed that on the other ones. Now, if we're going to do base 10 blocks, we're going to have to start with 37, and we're going to have to start with 28, and we're going to have to combine them, right? So let me actually, we don't really need this up here. I'll write it up here instead. 37 plus 28. So I need 3 10s and 7 1s, and then I need 2 10s and 8 1s. And then I'm adding, so I'm going to bring those two quantities together, right? Same thing we did in the previous chapters. Okay, bring those together, and then what do I collect at the end? What's there? 1, 2, 3, 4, 5. Don't do the slash yet. Don't do the slash yet. Just keep them as longs, right? Keep them as individual lines. And then we're going to have 1, 2, 3, 4, 5, 6, 7. And then 1, 2, 3, 4, 5, 6, 7, 8. Okay, so now we've brought the two together, right? And what I'm going to do is I'm just going to show an intermediate step here, because what I notice is that I have a collection of 10 ones. So what I'm going to do here is circle them. There's 10 ones right here, we'll say. That's 10 ones. So we can write that as 110. We can regroup. We can regroup. And then what we're going to get is this. We're going to get 1, 2, 3, 4, 5, 6. Wait, how many do I have? 1, 2, 3, 4, 5, and then 6. Okay, so there's 60, and then we're going to have 1, 2, 3, 4, 5 left over. 1, 2, 3, 4, 5. So the answer is 65. I think that's right. Was that the answer that we got? I don't remember. Ah, it is. It is. You see, once again, I had no idea what the answer was. I was letting the model lead me to the answer, because that's the whole point. The model is what gives you the answer, not the arithmetic that you already know how to do because you're an adult. The model is what helps you understand. So the thing I want to point out here is that this step is the critical step. You're just bringing together. That's all addition is bringing together, right? And then you regroup. And the regrouping process is this step going to there. And once you've regrouped everything appropriately, your answer just falls out, because it'll be written in terms of hundreds, tens, and ones, or thousands, hundreds, tens, and ones, and so on and so on. And that's really what's important. Notice that I never had to talk about carrying the one or anything like that, because there was no one to carry. This was a 10 being regrouped. And actually, if you go back here, that's exactly what's going on when that one gets carried. You're regrouping it and writing it as 110. That's exactly what's going on right here. In fact, I might even emphasize which one I made which one I made out of those ones. There it is. So you can do cool stuff like that with your models. All right, I'll leave this one for you all to try. So why don't you try this one? I'll give everybody about a few minutes. Go ahead, pause the lecture, and think about it. Okay. Next, let's try this one. Oh yeah, okay, so this one is called the left to right algorithm. And this one I put on here just to emphasize that you don't need to write anything in certain places or in certain columns or anything like that. You don't really need to do any of that. You just have to keep in mind what those numerals are representing. So this is the problem 568 plus 757. And what you can see right here is going from top to bottom. Let me draw that arrow there. What's happening here is this student is adding the hundreds and then the tens and then the ones. So let's draw that out here. 500 plus 700, because remember, it's not 5 plus 7, it's 500 plus 700 is 1200. So you just write 1200 underneath. Then you're going to do 60 plus 50. Remember, it's not 6 and 5, it's 60 and 50, and that's 110. And then you're going to do 8 plus 7, and that's 15. And then you can add all of those up. 1325, 1,325 right there. Okay, now you could do the same thing by going left to right. There's no rule that says you have to write it like that, and that's what's going on this way. So what happened here was this person got 1215. So what they ended up doing was they ended up doing that first, and then they just increased these two digits by 1 to accommodate the 110. There you go, to get 1325. So that's called the left to right algorithm. But yeah, just don't ever feel constrained by these structures, like you have to write in columns or you have to write in rows. You really don't have to. All right, so this is an interesting one. This one is called the lattice algorithm, and this is one that I want you to ponder about at home. Go ahead and take a look at this problem and see if you can figure out what the final answer is going to be and how that algorithm looks. Go ahead and take a few minutes and try it out. All right, now talk out loud about it. Say something out loud about what you've written down or what you're thinking about. All right, let's see how this works. Okay, so one thing that I noticed right away is that if you add up 7 and 8, you get 15. And if you add up 6 and 7, you get 13. And if you add up 5 and 6, you get 11. And if you add up 3 and 5, you get 8. And in this case, there's a 0 in front of the 8 just to fill in all of the little chutes, right? So the answer is found by adding diagonally. Oops, here we go. Adding diagonally. There we go. So let's try that out. Oops, let's try that out. Hey, all right. So going this way, let me use blue here. We're going to have 5 if you kind of add this way. And then 3 plus 1, that's 4. So we're going to end up with 4. 1 plus 1, that's 2. So we're going to end up with 2. And then 1 plus 8, that's 9. So we're going to end up with 9. So the answer is 9,245. And that's the lattice algorithm. That's the lattice algorithm for addition. You don't have to write the 0 out here if you don't want to, the same way that we would never write, for example, we wouldn't write 1,325 as 0, 10,000s, 1,325, for example. Okay, so that's the lattice algorithm. That's a fun one. Oh, yeah, already did that one. Okay, so, oh, that's right. Now let's talk about some subtraction algorithms, and then we'll call it a day after that. Subtraction is usually more difficult for students, and I find that it's more difficult for them, honestly, because they get locked into the symbols again. Subtraction in particular just seems really hard when you're locked into the symbols, and if you have no conception of the size of those numbers, it's really hard to calculate it. Hopefully, I'll be able to show you some neat tips and tricks here in this section. But let's go ahead and do this. Let's compute 266 minus 178 using base 10 blocks and the standard algorithm. So first thing is we have to use the standard algorithm. So if you're rusty on it, let's review it right here. We're going to do 266 minus 178. Now, the standard algorithm says that we can't subtract 6 and 8, or we can't subtract 8 from 6, because there aren't enough things to take away, right? So already this algorithm feels like, because remember those one students, they were using the negative numbers, and it was like boom, 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 and we were done. But the standard algorithm says you're supposed to go over here, you're supposed to go over to the next column and borrow, supposed to borrow something. This becomes a 5, and then we're borrowing 10, I think is what it is, right? I think that's what it says. And then this becomes 16. And now when we do the subtraction, we actually have enough to subtract from, right? So now we can say 16 minus 8 is 8. But we've come to that dilemma again. We can't take away 7 from 5, apparently. So we're going to have to go over and borrow some more. I don't know how many of these things we're going to need to borrow. We'll find out. Okay, so that's going to become a 1, and then this is going to become a 15, and then 15 minus 7 is also 8. And the answer is 88, because 1 minus 1 is equal to 0, but we won't write that leading 0 there. Okay, so that's the standard subtraction algorithm, and we'll see better ways to do subtraction in a minute, but I just want to point out how convoluted that algorithm is. That's not an easy algorithm to follow. It's not an easy algorithm to explain. There's all sorts of funky stuff going on, and it's hard to explain it to children because it's seemingly meaningless, right? That's one of the downsides to the standard subtraction algorithm is it completely divorces you from what's going on behind the scenes. And it's just symbol play. That's all it is. It's symbol play. What do you replace this symbol with? You replace it with a symbol from over here, and then you do this other symbol up here. That's not doing mathematics, right? That's not doing mathematics. So let's see if we can show what's going on here using the base 10 blocks. Okay, now let's see. If we're doing subtraction, then I need to start with a number and take something away, right? I got to take something away. So I'm going to start with 266. Oops. All right, now the standard subtraction algorithm says that I don't have enough ones to take away 8 ones, so I need to come over here and break apart one of these longs into 10 ones. So that's the first step. And I'm just gonna go ahead and, you could box it if you want. I'm gonna have to do some sort of like arrows and things like that just to save space here. But I'm gonna go ahead and say this. We're going to now have 100, 200, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6. There we go, right? And we could even label these things if you want. 100, this was 60, that was 6. Now we've got these 200s right here. Now we've got 50 and 10 and 6. But now we actually have 8 ones to take away. And that's what we're going to do next. We're going to take those 8 ones away. Oh, I wanted to use a different color than that. There we go. I'll do these ones. Why not? Okay, so here's me subtracting 8. Remember, you got to show that act of subtraction. And then once I take away 8, the next thing I need to do is I need to try to take away 7. Oh, but I don't have enough. I don't have enough 10s. Oh, wait, what am I saying? Take away 7? No, no, not 7. I need to take away 70, but I don't have enough 10s to take away 70. Okay, so now we got to go and like do this other thing, right? I'm going to have to go over here and break up one of these hundreds. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5. And then over here, I still have 8 ones remaining. Okay, now I can actually take away 70. Here's the next. This is me taking away 70 next. All right, and then what's left? Oh, actually, I only have to take away 100 next, right? That was the next step. And I can do that. I actually have 100 that I can take away. That was the very last step that the standard algorithm said to do, was to take away that last 100. So that's what we're going to do. We're going to take away this 100. And then, last but not least, we're going to be left with, oh, what have we got? 1, 2, 3, 4, 5, 6, 7, 8. That's 80, and then 1, 2, 3, 4, 5, 6, 7, 8, 88. There we go. So there's our final answer. Our final answer is 88. There we go. So this is how you would model the standard subtraction algorithm. That's literally how you would model it using base 10 blocks. You would do this physically with a physical manipulative in your class, and you can see that it would be really fun, right? You can spend days doing this type of stuff with your students. Just come up with a whole bunch of these types of problems and let them have at it with the base 10 blocks and separating them and regrouping. It's really, really fun. But this is how you would do it if you had to write it down, okay? Um, the first thing I want to point out about this is that it's a little bit convoluted, even the picture. it would be much nicer if we could just talk about taking certain things away in any order that we want. And it turns out that you can. You can. You can start by subtracting the hundreds and then subtract the tens and then subtract the ones. You can do that. You can break up a whole bunch of stuff at once. So it's much easier when you have that flexibility and you don't have to follow this strict algorithm. Okay. So yeah, if you want me to do something like that again, please ask and I will be more than happy to do it. All right, so now also note, we don't want to use the word borrow. Why do you think we shouldn't use the word borrow? Hmm. Hmm. What do you think? Well, usually this is around, right around the time when somebody says, you're not borrowing anything because you can't give it back. And that's exactly right. You're not borrowing anything. You're not borrowing anything because if you say borrow, what you're saying is that you're going to give it back at some point, but you're never going to give it back. There's no borrowing going on. There's just a regrouping. There's a breaking apart and a regrouping. That's what's going on. There's no borrowing. No borrowing, okay? So try not to use the word borrow because again, when you start saying borrow, students tend to start focusing on, I should use something other than black, start focusing on these symbols and borrowing the one and borrow the two and carry the one and carry the two. That's a bad path to go down. Trust me. I've been there. All right. Oh, so here's a much, much handier algorithm in my opinion. This is called the equal additions algorithm, and this is really fun. I'd love to do more examples in the the collaboration meeting too. So the way that I like to think about subtraction nowadays is as a distance. We'll talk about this more later too. But when you see an expression like this, 266 minus 178, what that really means is what's the distance between those two numbers? And the truth is that you're like you could imagine a number line, right? Or imagine my fingers. So let me do this really quick. Let me go to the camera. If I've got my fingers or my hands this far apart, and let's say this distance is the difference between 266, there we go, and 178. Well, that distance is a fixed distance between those two numbers. And if I were to shift both of them up, or sorry, shift both of them up, that distance does not change even though both of the numbers changed. Or I could shift it down. And that distance doesn't change even though both of the numbers changed, right? So this is essentially what the equal additions algorithm is doing. It's looking at the distance between your two numbers, the minuend and the subtrahend, and basically just saying shift it to somewhere nice that makes the subtraction easier. So check this out. That's what's going on right here. 266 minus 178. I mean, like, how do you feel when you see that? Because I feel like, I don't want to do that. I don't want to do the subtraction algorithm. Oh, let me get the slides back. I don't want to do the subtraction algorithm. No, no, don't make me do it, right? Well, you don't have to. Let's move the problem so that we're dealing with easier numbers. So in this case, what I did was I added 2. And I added 2 to both the minuend and the subtrahend. And in doing that, I ended up with this subtraction, which is a little bit easier, 268 minus 180. But maybe that's even a little bit too hard, right? And that's totally fine. It is hard. I don't want to try to take away 80 from 68. That makes my head hurt a little bit, right? So maybe we should shift it somewhere else. Maybe we should shift it somewhere else. And that's what I do down here. Check this out. Instead of just shifting everything up by 2, see over here I picked 2 because then that 178 would become a 180. That's why we picked 2 right here. I really should say these. So now, what if instead of doing that, we shifted it by 22? Let's do 22 instead. So I'm picking 22 because I'm trying to get that number to go all the way to 200 to make it easier. So if I add 22 to 178, I get 200. And if I add 22 to 266, I get 288. And 288 minus 200 is 88. That's super easy. Super easy to do. Super easy to do. So I think, yeah, okay, let me do one more example. I'm just going to come up with one off the top of my head. Let's find a subtraction problem that I really don't want to do. Okay, 5 minus 3. No, 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 I'm just kidding. How about something like, we'll say 321 minus 157. Okay, 321 minus 157. Don't use a calculator. Don't use the standard algorithm. Just pause for a moment and think about the distance, right? The fact that this is a distance between two numbers. And if we can shift those numbers to something that's more amicable or maybe nicer for us, then it'll make it a lot easier. Hmm. What should I shift it to, I wonder? Hmm. What do you think? What would you shift it to? Hmm. Hmm. Let's try this. Let's try adding, oh, I don't know, 13. Let's add 13 to both. So let's go like this. I'm picking 13 because I'm going to see if making this a 0, or if I should say getting a whole 10 there, makes it easier to compute. Let's try it. So now I'm going to end up with 334 minus 170. Oh, that's not so bad. 334 minus 170. That one I can split up a little bit more, right? I can split it up a little bit more. But I don't know, that 334, hmm, it's making it kind of hard. I don't know. I don't know. I don't know if I could do that in my head. Let's shift it some more. How about we add 30? Let's add 30 to both. Okay, and then what I'm going to end up is 364 minus 200. Oh, it's 164. Boom. There's the answer. 164. So you're allowed to do that. You're allowed to do that. You just have to keep in mind that you're shifting both of these numbers around on the number line. That's what's going on. So I highly encourage you to try that. I'll show you more examples if you'd like. I would be happy to. But what I want you to do right now is this. I want you to create your own subtraction problem and use this method. So yeah, let's go ahead and have another Dora moment for a moment here. All right. So what's next here? Oh, this is cool. So here are 3 student strategies for subtraction that were reported on in the February 2003 issue of Teaching Children Mathematics. So this is going to be another Dora moment where I want you to talk with yourself or talk with your group members. Remember, you got to talk out loud. The out loud part is important. Don't just think. Got to talk out loud. So here are 3 different ways of computing this difference: 872 minus 343. And this is my question to you. So take a fair amount of time and just think about these 3 methods. Try to make sense of what's going on there, and then ask yourself if they're valid methods. So go ahead and take some time, and I'll be back. All right, now take some time and talk out loud. Talk out loud about what you see here. Okay, and now let's talk together. So let's see. What's going on here? Ah, okay. So student A, I see what's going on with student A. It looks like student A is again thinking about our numeration system and thinking about place value, and they're subtracting away the hundreds first to get 572. Then they're subtracting away the tens to get 532, and then they're subtracting away the ones, I should say, to get 527. Is that valid? Absolutely, 100% valid, right? You believe me, right? No, no, you should never believe me. Never say yes, right? We should be able to show that this is actually true. Luckily, it's actually not too bad because the student is trying to compute this. Oops, 345. But we can decompose 345 into hundreds, tens, and ones because of our numeration system. And we can write it as 872 minus 300 300 plus 40 plus 5, because this is 345 right there. And now you can just subtract away the pieces. It's 872 minus 300 minus 40 minus 5. And so what happens next is they go 872 minus 300 minus 40 minus 5, which is 572 minus 40 minus 5, and then they do 532 minus 5, which is 527. And there's my validation. That is definitely a valid method. And here is the mathematical proof that it is valid. Keep doing that, student A. Brilliant. Keep doing it. Keep doing it. All right. Now let's take a look at, let's see. Let's go to student C really quick, and then we'll come back to student B. Student B is my favorite. Okay. So if we look at student C instead, sorry, let me delete those. Student C instead, they're doing something similar to student A, right? Except rather than break it up into hundreds and tens and ones, they just broke it up into hundreds, tens, and then ones. So essentially student C is just combining these two steps. And these are two steps that student A decided to break apart, which is totally fine, totally great. Great. Good job. Good job, student A. Good job, student C. Talk to each other about these two problems, student A and student C. I mean, I'm sure you could learn from each other, right? That's the idea. Okay, now let's look at student B. So student B is one of my favorites because it makes things very, very, how do I put it, less scary when you realize that you can do something like this. So this student essentially worked backward. This student worked backward. They realized that they could start at 345 and count up to 827. Or I mean 827, 872. See, dyslexia, I swear. 872. They could count up to 872. Go for it. They totally can. So how do you get a 2 in the ones place? What do you add to get a 2? You add 7. So if I add 5 and 7, I get 12, right? So it's going to go up and I'll have a 1 there. And then you can add 20, and that'll take you to, oh, that'll give you a 7 in the tens place, right? So you'll have 7 tens. And then you add 500, and that'll give you the 8 in the hundreds place, because you'll finally have 8 hundreds. So how many things did you add? Well, you added 527. So that's the distance between 872 and 345, or in other words, that's the difference between those two numbers, 527. Is that valid? Absolutely, it's 100% valid. 100% valid because it's essentially inverting the subtraction process and making it an addition problem. Definitely valid. Okay. Yeah, so what I want you to try at home is I want you to try computing or using these methods to compute 904 minus 367. So go ahead and take a little bit of time and work on that right now. All right, and now take a little bit of time to talk out loud about what you discovered and what you did. All right, let's see what's next. Okay, oh, I gave myself some space to do those. Um, all right, I guess that's it. Lucky, well, that's really nice, right? Oh, cool. So this wasn't too long of a lecture. That's it for lecture 4A, but let's take a look at activity 4A and let's see what you're going to be doing, okay? So let me go ahead and pull it up here. It's only on addition and subtraction. I can tell you that much. Do, do, do. Ah, here we go. So activity 4A, addition and subtraction algorithms. This whole activity is just practicing the algorithms that we saw in the lecture just now. So you're going to be using the expanded algorithm to compute addition. So use the expanded algorithm of addition. We did an example of that. Draw base 10 blocks illustrating this using the expanded algorithm. So show how the expanded algorithm can be modeled with base 10 blocks. So basically over here, you can do that addition, and then over here, draw the base 10 block representation of that operation going on. And you've got a whole page for that, so take as much space as you need. Use the lattice algorithm for addition to compute that. Uh, compute this using the standard algorithm, so just standard subtraction algorithm. And then draw base 10 blocks, illustrating the standard subtraction algorithm, which we did earlier in the lecture. And then use the equal additions algorithm to compute that as well. So it's kind of fun because you can get to compare the differences, right? So you can see the standard algorithm, see how it looks in base 10 blocks, and then see how you could have done it with equal additions. It's really fun, I think. Okay, so let me go be sure that that's it. Pretty sure that's it. Yep, next we're going to talk about multiplication algorithms. So we'll do that next time. All right, so I'll say goodbye and thanks again. Have a nice day.